I want to talk about the relationship between heat flow and the change in temperature in a substance. If we have a substance that's warming up, we're putting some heat into it, that is adding energy to it. How much the temperature changes depends actually on the substance specifically, as well as how much of the substance there is. So the concept we're looking for, the relationship we're looking for, is called specific heat, which we usually denote with C sub P. Okay? The sub P is a little subtle. There's actually two kinds of specific heat, one for constant pressure and one for constant volume. I'm not going to worry about which is which. We'll just say C sub P. If we put a certain amount of heat Q into our gas, our solid, our liquid, whatever, okay, how much it heats up depends on the mass, Cp, and then the change in temperature. Okay? So, if you want to think of it another way, how much heat it takes to raise the temperature by a certain delta T depends on how much material there is. You double the amount of mass of ice, the mass of water, you're going to double how much energy is required to raise it by the same amount. And then Cp. Cp has units of joules per kilogram times kelvins, or if you prefer, degrees C. They're the same thing. Okay? So your book has a table of CPs for different substances. So every substance you're going to have to look it up. Okay? For example, water, for a kilogram of water, it should be something like 4,184 joules per kilogram Kelvin. Okay? So this is what happens as the substance heats up when it's warming. But there's another thing that can happen along the way. At some point, a solid is going to start melting. When you get to melting, it actually takes a while for it to go through the full melting process. All those chemical bonds breaking, or all those bonds between molecules breaking, rather. Okay, so you actually hold at temperature for a while. So for example, with the standard example, ice. As you warm ice up and you get to 0 degrees Celsius, 273 kelvins, all of a sudden it stays at that temperature for a while as you add more and more heat. Okay, how much heat do you have to add to go from a kilogram of ice at 0 degrees Celsius to a kilogram of water at 0 degrees Celsius? That's called latent heat. For solid to liquid, or liquid back to solid, that's called latent heat of fusion. And we say Q is equal to mass times L, where L is the latent heat. You notice these two equations look a lot alike. The difference being this one has a change in temperature. The Q for latent heat doesn't have a change in temperature because temperature is constant. Okay? There's also a latent heat of vaporization, the heat needed to go from liquid to gas. Okay? There's a different L in these two cases, but the equation is the same. So you're going to have to go to a table and make sure you're looking for the latent heat of fusion if you want to go solid ice to water, for example, and the heat of vaporization to go from water to gas. Okay? But they're pretty simple. I'm going to show you a quick graph I'm going to draw. If we plot the amount of heat added against the temperature of the substance, we start somewhere with a solid where we haven't added any heat yet. As we add heat, the temperature slowly climbs for a while until we reach melting. Okay, and then it actually plateaus and stays level until we're all melted, and the temperature goes up again at some different slope, by the way. This depends on the Cp of the solid. This is Cp of liquid. Okay. Now, at some point, we're also going to reach a point where we're at the vaporization point. At that point, we're also level off for a while until everything's a gas now, and then we're going to go up at some other new third slope, Cp vapor. Okay? So, this is the heat we need to add to bring the temperature up from whatever it started off at up to the melting point. This is the heat we need just to go ahead and melt that substance. Okay? This is the heat we need to bring the temperature from the melting point here to the vaporization point up here, and then we've got another whole heat needed to vaporize, and then raise it up. So if we want to talk about how much energy it takes to take, say, a kilogram of solid ice at minus 20 Celsius and turn it into a kilogram of steam at, I don't know, 120 Celsius, we would have to calculate how much energy we need to get to here, from the low temperature up to the vaporization, or the melting point, melt it, bring it up from 0 Celsius to 100 Celsius, vaporize it, and then raise it that last little 20 degrees, okay? Sounds a little complicated, but just take it one step at a time and you'll always be just fine. All right, thank you.